All right, we are continuing with Unit 10, Infinite Sequences and Series. And today we are looking at Lesson 3, Convergence. So this idea of convergence with series, you're adding all of these terms together, and the idea is, can you come up with a sum? Not what is the sum, but can you come up with a sum? So if you can come up with a sum, then we say that the series converges. If you cannot come up with a sum, meaning it keeps getting larger and larger and larger and larger and larger, it goes to infinity, we say that the series diverges. So those are the two big ideas. Now, going forward, what we have for you are just tests. Does it converge or diverge? And there's a whole slew of tests, and I will upload these to Google Classroom. That's what we're using, Google Classroom. But there's a couple different forms on here to kind of help you just organize your thoughts. And I've got a couple options, but just pick one that makes sense to you. There's tables with all the tests on them. One of these, I have a flow sheet chart that might or might not help. And then this is just kind of another list. So it's whatever makes sense to you. This one got photocopied on blue one year. This is probably the one I use most often. But you just have to stop and figure out, do those series converge or diverge? So in particular today, we are going to consider positive series whose terms are all non-negative, meaning they're all positive. You could have zero in there. That's why they say non-negative. So we're looking at positive terms. So if the sum is a positive series, then the partial sums are bounded above and S converges. Partial sums are not bounded above and S diverges. Those are your two possibilities. We have the integral test. I think you'll like this one pretty well because it has something that we're familiar in there with us. Let a sub n equals f of n. So let each term equal a function where f is positive, decreasing, and continuous for all x greater than or equal to 1. So all of those terms are getting smaller and smaller and smaller. They're positive and they're continuous. We don't skip any. If the integral converges, then the series converges. If the integral diverges, then the series diverges. I know that seems like common sense. So show that, this is example 1, show that the series from n equals 1 to infinity of 1 over n diverges. So let's just check this out. If we have the terms 1 over n, what would that look like? Well, it's really 1 over 1, and then 1 over 2, and then 1 over 3, and 1 over 4, and 1 over 5, and 1 over 6, dot, 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 dot. The terms are positive. Check. They are decreasing. Check. And they tend to 0. They keep getting smaller and smaller and smaller. Check. So we are going to use the integral test. And the integral test says that we are going to integrate the function. So if each term is 1 over n, we say that our function is 1 over x. We have to turn it into a function. So we're going to integrate from 1 to infinity of 1 over x dx. Now, remember, infinity isn't actually a number that we can use in an integral. So we should have limit notation. As r approaches infinity, 1 to r of 1 over x dx. So this would be the limit as r approaches infinity. Now it feels like it's been a long time since we've done these, but if we integrate 1 over x, you get the natural log of x between 1 and r. So this is the limit as r approaches infinity of the limit, natural log of r minus the natural log of 1. I think I'm still in weekend mode. And the limit as r approaches infinity of the natural log of r, this should all be absolute value, minus the natural log of 1, but the natural log of 1 is 0. So this becomes the natural log of infinity. And remember, natural log graph looks like this. So as x gets larger, y gets larger. This is also infinity. We say that it diverges. We no longer use infinity for an answer. We now say diverges. All right. There's something called the p-test. Now it says recall the p-test from Unit 6, but I don't remember if we actually saw this anywhere. For the p-test, you have to have 1 over x to this exponent right here. If p is greater than 1, that integral will converge. If p is less than or equal to 1, it will diverge. The p-test is a big one. I know, it's got a funny name. We usually chuckle at it together. P-series is the third one down on my list. So example 2, does this following series converge or diverge? We're still going to use an integral test. Sometimes it helps. I'm a visual person when it comes to learning. So 1 squared is 1, 1 plus 1 is 2, this is 2 squared. And then we would have 2 over 2 squared is 4 plus 1, 5 squared, 5 squared. And then this would be 3, 9 plus 1, this is 10 squared. I mean, these terms are all positive. They're all decreasing, they're getting smaller. I mean, this is 1/4, this is 2 25ths, and this is 3 100ths. And they're getting closer and closer to 0. So I can use the integral test. So I'm going to set this up as an integral. I'm going to say the limit as r approaches infinity from 1 to infinity. These pieces kind of match here, of x over x squared plus 1 quantity squared dx. Now, what kind of rule do I need in order to do an integral here? Well, you need u substitution, where u is x squared plus 1 and du is 2x dx. Does everything match the way it's supposed to? Nope. So I need a 2 and a 1/2. You might also be solving for a dx. Again, that's another way to look at it. So this is the limit as r approaches infinity of 1/2 the integral from 1. By the way, this should be an r. The numerator is du, the denominator is u squared. How do we solve this? We bring u squared to the numerator, the limit as r approaches infinity of 1/2 u to the -2 du from 1 to r. Integrate u to the -2. Be 1/2 u to the -1 divided by -1 between 1 and r. 1/2. -1 on the top. I'm going to move the u back to the bottom from 1 to r. 1/2. -1 over r minus -1 over 1. If we're putting infinity in place of r, this is going to become a 0. So I've got 1/2, 0 plus 1. My final answer is 1/2. Now, it does not, let me clarify, it does not mean that the sum is 1/2. What it does mean is that because this converges to a value, it doesn't matter what value, this series converges. So because I got an answer for my integral, the series converges. I just made a mistake. Did anybody go through this with me and say, hey, Mrs. Charnley, you're wrong? Definitely still in weekend mode. Boundaries. Remember, x boundaries and u boundaries. I left these as x boundaries here. They really should be u boundaries. Now, the convenient thing for me is you have two choices. You can either leave all of these as x's and put an x back in here, which is what I think I'm going to do here. Or you could switch all the boundaries into u values. So the lower boundary would be a 2 and the upper boundary, when you put infinity in, is still going to be infinity. But let's do that. Let's change the bottom. So I'm going to put my x value back in, which is this one, x squared plus 1. So I moved this to the bottom, and then at the same time, I put the x values back in. So now I can put those in. So this would be r squared plus 1. And then this would be 1 squared plus 1. So this is actually, whoops, drop my pencil, move the sheet. If I put infinity in for r, that's still 0, but now this is a 1/2. So I get a 1/4. So the value of the integral gives me a 1/4. Again, not the sum. It is not the sum of those terms. Remember, the only sum we can calculate is for a geometric series. You can't do it for anything else. But we can say the series converges. The series converges. I know, these are crazy. I know. The next one I have for you is the comparison test. If we have a series A, which is less than or equal to series B, but they're both positive, if B converges, then A also converges. But if A diverges, B also diverges. But if A converges, it doesn't tell me anything about B. And if B diverges, it doesn't tell you anything about A. What are they talking about? Again, I need pictures. So think of them like functions. If you have, here's series B. Here's B. Here's all the terms of B sub n. They converge. They're getting lower and lower and lower. And we know that series A is less than series B. It tells us so right here. If A is less than. So if B converges, then A also does too. So if B gets smaller and smaller and smaller, then A has to get smaller. It's kind of like that squeeze theorem idea. Very, 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 very similar to that squeeze theorem idea. However, if we draw this a little bit differently, if A diverges, so A is getting bigger, bigger and bigger and bigger, goes to infinity, and we know that B is always larger, then B has to also go to infinity. It has to diverge. If the smaller one diverges, the bigger one has to diverge. It's going to push it bigger and bigger and bigger. But if B gets larger, that doesn't tell me anything about A. A could be getting bigger, A could be getting smaller. But if B diverges, it doesn't tell me anything about A. And over here on the first one, if A converges, it doesn't tell me anything about B. Process that for a second. If the bigger one gets smaller, the smaller one has to get smaller. If the smaller one gets bigger, the bigger one has to get bigger. Crazy. I know. They're crazy. Let's look at example 3. We are looking at a comparison test. All right. I'll be perfectly honest. I don't like these. We are going to compare to, and this is the part that you're going to be uncomfortable with, 2 to the negative n. You have to make up the second series. You have to make it up. So how do you make it up? It has to be similar to the first one, but a little bit more straightforward. So get rid of any inequality or factorials. That's not an inequality, that's factorial. Get rid of any factorials that you can. And then decide which one's bigger. So sometimes the new one is bigger. Sometimes the new one is smaller. So make sure you know what you're talking about with these. In this particular case, 0 is less than or equal to 2 to the negative n factorial, which is less than 2 to the negative n. I guess I should get rid of the equal to's. How do you know? Well, pick a value and test it. So I'm going to say n equals 3. So 0 is less than 3 factorial is 3 times 2 times 1. So this is 2 to the negative 6th, which is definitely smaller than 2 to the negative 3. Right? It would look like this. Okay. So the new one is larger. So if I look at these, I am going to say, here's my new one. It's the series from n equals 1 to infinity of of 2 to the negative n. I want to make that a positive exponent, so I'm going to move it down to the bottom. 2 to the n. Now, remember those exponent rules I mentioned on geometric series day? This could be 1/2 to the n, because take a little detour. It's 1 to the n over 2 to the n. You can group the 1 and the 2 together. Now, if it's in this particular form, this is a geometric series. Geometric. So what did we say about that ratio on the inside if it was geometric? R equals 1/2. 1/2 is less than 1. Series converges. And in fact, I should probably say that, be very specific. N equals 1 to the infinity, 2 to the negative n. This converges. So because this converges, my original, and it's larger. So because the larger one converges, the original also converges. That's a mouthful. So what does this answer look like? Because, I want to make sure I get all the words in here. Because my new series converges, then n equals 1 to infinity of 2 to the negative n factorial also converges. By the comparison test. Ta-da. Okay. That's a lot going on. Let's try another one. Example 4. Let's pick something to compare to. What are you going to compare it to? It's going to be similar, but what can you get rid of? You're actually going to get rid of the natural log. Get rid of that. So compare it to 1 over n. Now, 1 over n we just talked about a minute ago with the integral tests. And there's another way we can do this one. So let's line all these up. We've got 0. So what's smaller, 1 over n or 1 over natural log of n? 1 over n is going to be smaller, believe it or not. And that's because your natural log curve increases. It passes through the 0.10. And it increases, but it increases slowly. So for example, if you're out here at 4, where's the natural log of 4? The natural log of 4 is 1.38. So your y value is less than your x value. When we're greater than 2, notice this one starts at 2. It doesn't start at 1 because you're dealing with zeros, so that's why it starts at 2. 4 n greater than or equal to 2. Okay, so we have 1 over n. We know that's the smaller one. So we don't want to necessarily show that this converges. That won't prove anything, but we could show that it diverges. So I'm going to give you 2 choices. We can say that n equals 2 to infinity. 1 over n diverges by the p-test. That is the easiest one to identify. Your exponent right here is a 1. If I go back to the rules for the p-test, diverges when p is less than or equal to 1, and it's equal to 1 here. So this diverges. Or n equals 2 to infinity, 2 to infinity of 1 over n. You could set this up as an integral, the limit as r approaches infinity, 2 to infinity of 1 over n, dx. If we integrate that, that's natural log of x. We're dealing with, goodness gracious, 2 to r, the limit as r approaches infinity. So this is the natural log of r minus the natural log of 2. The natural log of r is the natural log of infinity minus natural log of 2. Well, the natural log of infinity is still infinity. Natural log of 2 is some number, infinity minus some numbers, infinity. This diverges. So we can actually say that this diverges by integral tests. So we have two ways that that new series diverges. So because the new one diverges, we must say that n equals 2 to infinity 1 over natural log of n all diverges by comparison tests. Oh, these are a mouthful. I know they are. I know they are. Be patient with yourself. Be very patient. This is going to take practice. This takes a lot of practice. The limit comparison test. Last one for today, I'm pretty sure. 5 and 6, yes. Let A and B be positive sequences, and you want to find the limit of A over B. If that limit is greater than 0, A converges if B converges. If that limit is equal to 0, B converges, then A converges. Oh my goodness. All right, so let's try one of these. Show that the series converges. Show that series converges. And determine if converges. All right, don't mind my handwriting here. All right, limit comparison test. So for example 5, again, we are showing that this series converges. So you have to have something to compare it to. And I know that that can be a tricky idea. So start out with the original. So n squared over n to the 4th minus n. And then you ignore anything that's not significant. So in that denominator, I see that n that doesn't matter. So I've got n squared over n to the 4th. Remember, we're going to an infinity. So think of the things that don't matter as you go to infinity. And this would simplify further to 1 over n squared. So that is what we are comparing to. Now, look at the new one, your b. So n equals 2 to infinity 1 over n squared. This is your b sub n. Ask yourself, does this converge or diverge? Well, this one converges by the p-test. And again, we're looking at this exponent right there. The exponent is greater than 1, so it converges by the p-test. So for the limit comparison test, what we need to do is find the limit. Let's switch up colors again. Find the limit as n approaches infinity. Put the original in the numerator, n squared over n to the 4th minus n. The new in the denominator, 1 over n squared. So we have, this is a and b for the terms of our series, b sub n. There we go. And what we're going to do is calculate the limit. So if I have a fraction divided by a fraction, you know that's multiplying by the reciprocal. A lot of algebra rules in here. N to the 4th minus n times n squared over 1. And if we take this a little bit further, this becomes the limit as n approaches infinity of n to the 4th over n squared, n to the 4th minus n, excuse me. Remember, we're looking at the limit as n approaches infinity. So you could do L'Hopital, you could divide everything by n to the 4th, but you are going to wind up with a 1. This is a 1. So because we have a limit, come back up here to the rules, a limit greater than 0, then A converges if and only if B converges. Well, back here we said that B converged. We have a limit value that's greater than 0. Therefore, A will also converge. So we can say that n equals 2 to infinity, n squared over n to the 4th minus n converges by the limit comparison test. Okay, good. One more here. Example, determine if this one converges, 1 over the square root of n squared minus 4. So again, pick the original, and remember you're going to infinity, so think about what doesn't matter. that -4 is insignificant. So I've got 1 over the square root of n squared. Well, the square root of n squared is 1 over n. So this is what we're going to compare it to. So we have, here's our b sub n equals 3 to infinity of 1 over n. Well, does this one converge or diverge? We've discussed this one twice already. This one diverges by the p-test or the integral test. It diverges by either one. So now we have to do a limit comparison. We're going to compare. So remember, we're looking at the limit as n approaches infinity. The original goes in the numerator. 1 over the square root of n squared minus 4 over the new one, 1 over n. This is our a sub n over b sub n. We're finding the limit as n approaches infinity. So we need to multiply by the reciprocal. So I've got 1 over the square root of n squared minus 4 times n over 1. So if we look at this, we've got the limit as n approaches infinity of n over the square root of n squared minus 4. Now, what is this equal to? Originally, when we did these infinity problems back in Unit 1, way back in September, we said don't worry about the things that are insignificant. So in this case, the 4 is insignificant. You have an n in the numerator, and that square root of n squared in the denominator would turn into an n, so n over n is equal to 1. So let's talk about one other way you could look at this. The limit as n approaches infinity, you can actually divide everything by an n squared. So n over n squared, well, dividing by n really. If I want this to be n squared over n squared minus 4 over n squared, then I have to divide the top by n squared inside of a square root. Are you with me? So the numerator would become a 1. This would be the square root of 1 minus 4 over infinity is 0. So this is 1 over 1, which is 1. The old textbook we used to use did a lot of that, but we get a 1. So let's talk about this. If the limit is greater than 0, which it is, A converges if and only if B converges. This one actually doesn't say anything about diverges, but they do match up. So I'm going to come over here to my list here, limit comparison. And I actually like this definition better. If the limit of A over B, and you can't quite see it, is equal to C for some C greater than 0, then both the series converge or diverge. So whatever B does, A will do as well. So I like this definition better. I'm going to add these in your resources. So let me come up with an answer here, and then we're all done for today. So since the series diverges and your limit is greater than 0, then the series, I probably don't need to write the word series, the original one, n equals 3 to infinity, 1 over the square root of n squared minus 4 also diverges. All right. You're going to have questions. You're going to struggle. You're going to struggle. It's okay. Ask me for help. Ask Mrs. Oates for help. Look up videos on YouTube. Do whatever you got to do. Check your answers. But this is the rest of the BC material. I can't tell you that it's only 1 or 2 questions on the test. It's a significant portion of the BC test. So make sure you're asking questions about these. All right. Good luck, guys and gals.